Testing, testing, testing. Is everything ready to go? Testing again. Testing on a different setting. This setting is much better. All right, let's try that. Okay. Happy Monday. Today we're going to be looking at a paper called QuestSim, Human Motion Tracking from Sparse Tensors with Simulated Avatars. This is a paper coming out of Reality Labs Research, which is Meta's VR division. Meta, of course, being formerly Facebook. Published 20 September 2022, so roughly maybe a month ago. So here we go. If you're joining for the first time here, we're using what's called PaperPile to organize this paper and track it and keep track of highlights. Okay, so in this picture here, we have a picture of these researchers, right? I'm assuming these guys are Alexander, Jungdam, and Yuting, these guys in these pictures here. And really what they're trying to do is match the position of this human avatar to the position of themselves in the real world. So there's a couple different bars here. In simulated environments, people will have these little three bars that indicate the Cartesian directions of a tracking frame. So one way to remember is that XYZ is usually RGB. So X is red, R. G is Y, which is green, and then blue is Z, which is out. And of course, VR headsets, in particular this one, the Quest 2, has kind of the HMD, which is the glasses part, and then two individual controllers. And then here we can see on this person's hand the position and orientation, right? 6-dimensional XYZ, and also the rotation angles of each of the controllers and the headset. And of course we see the foot has a single dimension, maybe how high off the ground you are. Position and orientate. Okay, reconstructed from the position and orientation of a headset and two hand controllers. Okay, so in this left image, you have this entire pose is simply reconstructed just from the position of the controllers and the headset, and on the right here, it's reconstructed from the headset only, so all you have is the position of the headset. Same policy can track users of different sizes, so you don't need to have all these different hyperparameters. Motion is simulated, which gives access to dynamic quantities such as normal contact forces. Okay, interesting. So red line on the ground is the contact force. So here, when you're jumping and you're on one leg, you have a much higher contact force of this foot against the ground versus when you're just carefully walking over, and more of your weight is potentially on this foot here and maybe on this heel. Real-time tracking of human body motion is crucial for interactive and immersive experiences. Very limited sensor data, right? All we have is just the position of these controllers and the position of the head-mounted display or head-mounted device. Is that a rename of HMD? In this work, we present a reinforcement learning. Okay, interesting. So this is a RL framework. Takes in sparse signals from an HMD into controllers and simulates plausible and physically valid. Okay, so this is basically the meat of what this algorithm does, is taking the signal from the HMD and the controllers and trying to convert that into pose, right? Position and orientation for an entire human body. Okay, so they use high quality full body motion to dense supervision during training, right? So they have a data set of real high quality full body motion. Surprisingly so. Okay. So this is in the previous Oculus Connect, which was roughly maybe a week or two ago, they showed that in the new Quest Pro, and I think in kind of the Quest 2, they will retroactively add legs to the avatars, and these legs aren't in any way tracking your real legs. What they're simply doing is they're determining the position of your legs based on the position of your head and your hands. So I assume that's what this kind of software or research project eventually led to, is that demonstration. Okay. This is the SIG graph. SIG graph 22, conference papers. Okay, this is in Korea. Okay. Promise of AR and VR. Look at that, they define that for you. Augmented and virtual reality. Richer forms of self-expression and social experience. Accurately capture. Enable this. We need a sensor that faithfully reproduces the boat. We need sensors and methods that reproduce the full body motion of a user real time. Yeah, you want your avatars in the virtual world to be as accurate and true to your real world body motion as possible. Optical marker based solutions, right? So mocap, as they're also known, right? Something like this, where you're wearing one of these suits that has a ton of tracking points on it, and you can track every single one of these points with cameras that are all over the corners of the room, and then you can use that to drive a simulated human. Are often used in industry or research labs that require high precision. However, the setup is complex. Yeah, you need multiple cameras throughout the room, as well as attaching and calibrating markers on the users. There is such a thing as markerless motion capture. However, you still need these outside tracking cameras. Yeah, so moving between rooms or having a large occlusions also matter a lot, not just in the markerless motion tracking, but also in the marker-based solutions. I have here an espresso shot with MCT oil, and I'm going to blend it. And that's how you get the energy for the day. All right. have water in a fellow cup. Okay, so we have markerless, marker-based solutions. We also kind of have potentially wearable sensors where, in a sense, actually, the controllers are a wearable sensor, right? They have a IMU, which you also have in a phone, which allows you to get the linear and angular motion of a device. And from that, you can extrapolate kind of the position, right? And sometimes, because you're kind of extrapolating this position from acceleration and velocity, you get to this kind of drifting problem where an object will slowly drift over time because you don't actually know with 100% accuracy what the position is when all you have is the acceleration and velocity, right? So the way that this is done is usually you have something which is known as a Kalman filter. So a Kalman filter is taking a bunch of measurements over time from a bunch of different sensors, and each of these sensors is going to have some noise and inaccuracy, and then you combine all of those together and you can get a position, the actual position of the object, right? So maybe something, I'm trying to see if I can find a good picture that would represent this, but these pictures are a little bit too complex. They make it seem like it's more complex than it actually is. So really all you're doing is, this is a good example. For example, this is the probably the original signal is this black part here, and then this red part would be the Kalman filter, right? So the Kalman filter is going to give you a smooth estimate that doesn't have the noise associated with that. So when you have IMU and then maybe you have some camera information, SLAM, you can use both of those estimates, feed them into a Kalman filter or something similar like that, and it'll give you a more smoothed out global position and orientation of the headset and the controllers. Yeah, and then kind of the promise of inside-out tracking where, because you don't need these external cameras, you can move the device across rooms and you can have more complicated occlusion type setups. Yeah, so there's no information from the lower body. There are some people within the VR community, they put their Vive trackers on their actual feet. This is something that's relatively common, and this is a way of not only having the controlling or the tracking on your hands, but now you can also have it on your feet. These are outside based trackers though, where there is an external camera that's kind of looking at your body, maybe in the corner of your room, and that's how it can tell that the position of these tracker objects. The space of all possible human poses is vast, and they say that, right, trying to find the right leg position, you get all kinds of things such as jitter, foot skating, and unstable contacts, right? So foot skating might be that your foot kind of shifts on the ground, is kind of magically floating around. Incorporate an off-the-shelf physics simulator to tracking to constrain the solution space. Okay. To physically valid poses. Okay, so this is interesting, right? I didn't think this paper was going to go there, but basically what they're saying is that you have the position of this headset and the controllers, and you can maybe figure out the pose, but then we're additionally going to provide a kind of regularization or an additional constraint where we're going to look at a simulator, a physics simulator, right? Something that takes into account the mass and the momentum and the kind of collision space of objects, and we're going to use that to further constrain the solution space such that we have a physically valid pose. We'll have to figure out what that means, right? Does that mean that it's balanced? Does that mean that the foot is always in contact? Is there weight to the human? Like how is that physics information really used? Sparse upper body carry enough signal to predict lower body pose. Okay, so simulated environment can be used. Physics is a sensible prior when reconstructing the aspects of the pose. Boo Boo, you want to come check out your stream? That is Boo Boo. She's making an appearance on the stream. And then she's leaving. She's got important cat stuff to do. Okay. Generating 3D full body poses based on camera images can be used for motion tracking. Right, so pose tracking, computer vision. So there is a ton of previous work on using a 2D image to get a pose. And these are pretty good nowadays. So it used to be that just from a forward-facing 2D image, you would still have problems. But nowadays, with models such as open pose, dense pose, like you can track very complicated scenes with many, many humans, a lot of them being partially occluded, and you can get a full 3D skeleton for them. This is actually what they're referring to here with markerless motion tracking, is basically relying on these type of sensors to do that. There's still some issues, and if you really want high fidelity, you still want to use a motion capture suit, which is why in like movies and for video game animations, people who are professional will use motion capture suits, but eventually that will go away when these type of models become even more strong. Not that they aren't strong already, they're already pretty good. Okay. Parameterized and differentiable statistical human body known as simple. So we've seen this on this channel again before, but this is a realistic 3D model of the human body. You'll see this in these papers. It's basically kind of like an open source version where they create a mesh, right? The tracking will only give you what's known as a pose or a skeleton, right? The position of individual joints along a body, but then you have to basically wrap this triangular mesh, right? This mesh made out of little triangles and wrap it around that body. And normally there's a bunch of kind of hand designed work that goes along with it, but simple here is, you see, look at the deformation, especially around the knees and the elbows is usually where you can tell it the most. It's actually pretty good. So the way it wraps that mesh around. Body key points, these are the position of, these are the elbows, those little dots in that skeleton. Yeah, if every frame is reconstructed individually, continuity between frames can be difficult and cause pose to jitter. So this is actually a problem with all deep learning based computer vision. A lot of it has this issue where the algorithms are designed to run on a single frame kind of independently or not conditioned on previous frames. There is work where people use more sequence based architectures and put constraints on the pose of one frame so that it can only move a certain amount from the pose from the previous frame or something like that. But this is why when you see videos of, for example, something like a bounding box detector, the size of the box usually jitters, and there might be a frame where there's no box and then the box comes back. Okay, IMUs, inertial measurement units, right? They measure the inertia. Acceleration signal, right? They give you the acceleration. From that you can get the velocity, and then from the velocity over time you can get the position. Okay, so mocap data paired with IMU signals. If you have a bunch of mocap data and you have the IMU signals, right, then you can basically use deep learning to kind of predict one with the other, right? Train on the IMU signals and train to output the mocap data, and then that gives you enough corresponding pairs between these two data distributions to train a model to project from one to the other, which is basically all you're doing in deep learning, right? Or supervised deep learning. Huh. This is cool. I've never heard of this. Sensors based on EM fields have also been used to reconstruct full body poses. So that's pretty crazy. What is this? Manuel Kaufman, 3D human. That is human pose estimation from sparse electromagnetic trackers. Human pose estimation from sparse electromagnetic trackers. Okay, so it seems like these trackers are yeah, I mean, this is a crazy setup here. Like, look at how many external cameras you have. These are Kinects, which actually is what this camera here is. This camera here that I'm using is a Kinect camera. In fact, you can actually even I can switch it to this. This is the infrared version, so you can see all these little dots that are being projected here. That's how you get the depth. There is no depth for this, of course. Okay, so these little electromagnetic sensors are on the elbows, on the knees, on the calves, and that's kind of how they're getting that. I think the full camera external setup is just to be able to track so you know what the ground truth is, or you at least have a pretty good estimate of what the ground truth is, and then the EM sensors are just another way to do it. Okay, that's kind of cool. Let's go back to the paper here. HMDs, head-mounted devices, methods that generate. Okay, so variational autoencoder, right? Where VA is first learned with all poses, and then the decoder is combined with another encoder which uses IMU signals. So variational autoencoders are based around this idea of taking a signal and then forcing it, compressing it into a small latent dimension, right? or a feature space, right? And then uncompressing it back to the original signal. And the compression and uncompression is done with deep learning, right? With neural networks. And basically the loss is you want the reconstructed signal to match the original signal. And it is kind of crazy how for a lot of different signals, right, whether that's images or here IMU signals combined with poses, there exists a feature space, right, a manifold that is much lower dimensional that allows you to compress that data distribution in a way that is as lossless as possible, right? So something crazy to think about. Okay, so there's a more recent here 2022 paper where they use transformers, and I guess that probably actually has better performance than this paper, to be honest. So the way they kind of poo-poo on it is saying that these don't enforce physical constraints, right? So one way that the authors of this paper kind of want to set themselves apart is by kind of their physics, right? This argument they were making before where, hey, if we have a physical simulator, we can look at these poses and see if they make sense from a contact and rigid body motion perspective, and that allows us to remove foot skating and jitter. So they're kind of focusing on the problem that they can solve. Here we go. This is exactly what I was just describing. Yeah, so the problem is under constraint, right? There's a lot of solutions. Many solutions fulfill the sensor constraints, right? But only some of them are going to be physically possible or, I guess, believable. Okay, here's a couple other papers that also use this kind of idea, using a physics-based optimizer as a refinement process to further improve motions generated by kinematic methods. They're not enforced as hard constraints. So the authors of this paper are even more puritanical about the physics filtering down the large set of kinematically valid poses into a much, much smaller set of physically valid poses. Okay, we build much of our work on RL-based imitation learning, which adds a physical simulator as a final step before the pose generation, thereby enforcing physics as hard constraints that cannot be violated. Okay. Imitation learning with reinforcement learning is a type of reinforcement learning where the exact output given a certain input is known, right? So it's kind of like a form of supervised learning where you already know the optimal policy. The controller joint angles. Break dancing. That's quite a hard one. right? These large mocap datasets are very appealing to kind of the whole motion tracking and human animation space because, right, deep learning works very well because of the large amount of data. So these data sets that have been accumulated over time of people doing all kinds of animations in mocap suits are a great way to kind of reduce the space of all possible human positions into those that kind of make more sense, right? Yeah, this is even cooler, right? Where I think in the future here, we're still like the community's still really just struggling to get something that works extremely well, right? Something that's like very, very accurate and works very clean every time on no matter what human. But I imagine eventually there will be a point in which you can kind of, similar to how image and video generation, you can apply specific styles, right? You could say generate a picture of a keyboard in the style of Van Gogh. Eventually you'll be able to say, hey, generate for me a animation of someone picking up a cup, but in the style of, I don't know, a bodybuilder, and like then the person just kind of more awkwardly grabs the cup, or in the style of a toddler, and the person a little bit more fumbly when they grab the cup. So I think the styles for animation is something that's going to be cool in the future. Okay, monocular just means one camera. Egocentric just means the camera is on the person, right? So it's like either a GoPro on their forehead or it's on their chest or something. Okay. They're setting themselves apart from these. They're saying, hey, we're not even using video data. All we're using is 6DoF. So all they're using is the 6 degree of freedom state of the headset and the controllers. And right, because this is a simple, relatively low dimensional simple input, you don't need to have a pre-trained convolutional neural net at the beginning to encode an image. You don't need to have transformers. Although I'm sure transformers would have actually worked better in this approach because, right, you can, this is fundamentally like a problem over time. It's more of a sequence. I feel like it makes more sense, and I think we've already looked at some papers that you're using transformer-based architectures for this type of stuff, but because they have a relatively small input here, and again, of course, all research projects have to have a beginning and end, they can just use a simple MLP, which just means a bunch of consecutive layers of neurons, right? Okay, RL background. So as with any RL paper, there's going to be a little section here where they explain what reinforcement learning is. Yep. So find a policy pi to maximize the expected discount return. So return is just the reward, right? So in a video game, it might be how many coins you collect, and discounted return basically just means that rewards coins that you collect way in the future don't matter as much as coins that you collect closer in time. So if I perform an action, right, which is my policy is the neural network or the algorithm that determines what my next action is given a state, right, or a current observation. The action will be rewarded for stuff that happens sooner more than stuff that happens later, and that trade-off is known as the discount factor, right? So if 3 hours from now I eat a cupcake, that shouldn't matter. That shouldn't count as much as eating a cupcake now. I don't know. That's kind of terrible explanation of what a discount and return is, but that's roughly what it is. And here, right, this goal is you're trying to find a policy pi naught where the expected value of that policy as it goes, or the policy in pi naught, right? Or maybe, what is this t here? Is that just the trajectory? Yeah. So the expected this of the trajectory from the optimal policy is the sum from 0 to time t, right? So all the steps in that particular rollout of the discounted to the t, right? So the further you go in time, the less it's going to count, and then the reward at that time t. Current policy. And then this is just kind of telling you the probability of a trajectory tau given a policy theta is the probability of the state 0, right? So how often are you in that state? Or what is the probability of being in that state? And then this big pi here just means multiplication, right? Because these are all probabilities of the probability of the next state given the current state and the current action times the policy outputting that action for that state. Where P S naught is the initial state distribution, right? So S naught is the initial state. And with all these things, it's usually not a specific number. Usually it's the numbers that parameterize a distribution. So rather than being S naught being like position x equals 1, what it would say is S naught is actually two different things. It's the mean of a normal distribution and its variance. So rather than saying S naught or S0, the initial state is just position x equals 0, you're saying the initial state is a normal distribution, right? A Gaussian curve centered around a specific mean and having a specific variance, right? A specific width. The probability is used to calculate the expectation, which quantifies the expected return. Okay, so they're using proximal policy optimization, PPO. This is a pretty common reinforcement learning algorithm. It's used as a baseline. It's implemented in a lot of different reinforcement learning frameworks and libraries. So this isn't actually a super advanced RL. So it's interesting to note, you know, because you have here kind of a top quality research lab in Meta, but they're using a multi-layer perceptron as their architecture, and they're using PPO as the reinforcement learning algorithm. So there isn't a ton of novelty here based on the architecture and the algorithms that are used within this paper. It's a lot of this work is going to be elsewhere, right? Integrating all these different pieces together. So this is kind of more of a actually solving the technology problem paper rather than trying to find a specific architectural little knob that you can turn. I'm going to go to the bathroom real quick, take a quick second. I'll be back. All right, and we're back. Hope you guys like that intermission. That's a pretty cool one that I spent a little time working on. Okay, so the goal is to reconstruct the full body pose from sparse user observation. So defining here user as the sparse observations, and then the output pose S of t. So user is going to be the 6 degree of freedom state of the headset and the controllers, right there. And S of t is going to be the final position generated by physics simulator. The simulator is driven by joint torques, right? So at each joint, right, maybe this elbow joint, you're going to have some torque. And torque is a type of force, right, which means that it's just a function of the mass and then also the acceleration. And then from the torque, you can kind of get to something like an acceleration, and from the acceleration, you can get to something like a velocity, and then from the velocity, you can get to something like a position, which would, in this case, would be a joint angle. Neural network themed policy. So the policy here is their multi-layer perceptron. We train the policy to produce torques. We use a scalar reward R of t, producing a pose. Okay, corresponding ground truth pose from a motion database. So, okay, they're basically doing supervised learning. They call this imitation learning here. Where was this? In the reinforcement learning section. They called it imitation learning, but honestly, this just feels like supervised learning. You have a motion database, and you're training your policy to imitate that database. They're framing this as a reinforcement learning problem. Yeah, it's interesting how the similarities between kind of supervised learning and imitation learning, and I guess it's just because they're using reward and PPO. The policy to use this internal state to decide on optimal actions. Okay, so interesting. So earlier we were talking about using something like a recurrent neural network or a transformer. You would obviously use transformers and not RNNs because it's 2022, not 2018. And the reason you would do this is because, right, these poses really are better represented as poses over time. But the way that they do it in this paper is they actually take the output and they feed it back into the policy. So the policy is not just aware of the user observation user here, but it's also given OSIM, which is the position that it outputted kind of the previous time step or the current position in the simulator. So it's constantly conditioned on the position, both the position of the head-mounted display, but also the position of kind of the previous step. So this allows it to be kind of internally, this allows it to be more smooth, more consistent, because it knows that it can't move that far from its current position. Right, so there's kind of 3 sections here. There's the observations coming from the simulated character, OSIM here. The sparse observations coming from the sensors worn by the user. That's OUser here, right? So OUser, and then OSIM, and then the scale of the user. So there's some other scale somewhere here that's getting fed into this policy. During inference, this network produces torques for a physics simulator that generates the pose. Okay, so the output of this simulation or of this entire policy is not joint angles but torques, and those torques are used to drive a human body in a simulator, and then the final joint outputs of that human body in the simulator are then what you would use for tracking. 33 degrees of freedom for the avatar. That is quite a lot. Actually, maybe not. No. Because I know that Coco human pose, right? This is a famous standard for the trees, for these kind of skeletons used in motion tracking and pose detection. Coco itself has 32 different positions, but each of these positions might be three-dimensional, right? The position of the knee, right, can be the three-dimensional or even six-dimensional position of that knee. So if there's whatever 32 different potential key points, each with 6 dimensions of freedom, 33 degrees of freedom is actually not a lot for a simulated avatar. Joint angles, and then joint angle velocity. So observation sim of Q is the actual angles, Q dot is the velocity, and then Q double dot will be the acceleration, if they actually ever do that. The Cartesian positions, X. So what do they mean by joint angles versus Cartesian positions? So joint angle would be kind of the angle of, for example, this elbow, right? Like maybe this is 90 degrees. The Cartesian position of this elbow, though, is how far it is from the ground, kind of relative to the center of the space, or maybe the center of the human. So this is more the XYZ position of the angle, and then this is the actual, or this is the XYZ position of the elbow, and the joint angle would be the actual angle of the elbow. All respect to a frame S, which is located on the floor below the avatar. Okay, so the kind of global inertial reference frame rotates according to the heading direction, which allows the policy to learn torque mappings independent of the heading direction. So this S frame, from which all of them are in reference to, it rotates depending on the direction that this person is moving in or facing, such that the torque mappings are independent of that direction. Yeah, that's the problem when you start conditioning policies on parts of the state, right? Is that it starts kind of overfitting, or not overfitting, but it starts to think that some parts of that state matter more than the others, you know? If it just so happens that in your data set, whenever it's moving to the left, you're always kind of pulling your elbow up, but then whenever you're moving to the right, you have slightly more data where it's pulling the elbow down. The neural network is smart enough to pick up on that, right? And it'll notice that statistical pattern in the data, and it'll say, hey, if you're moving left, it's actually, you're more likely to be moving your elbow up versus down, right? And then that's not really something that you would want. And ideally, you would have a balanced data set that has as much elbow up and as much elbow down in both directions. So in order to fix this kind of potential problem with bias in the data set, they're going to basically rotate the inertial reference frame depending on where you're looking. Link orientation. Okay, interesting. So the link is just basically, for example, this forearm. So if that's the link between the elbow and the wrist. And they're going to take the rotation matrices of these links, which are 16 by 6 rotation matrices, and then they're going to just basically take the first two columns and feed that into the network as well and call that OSIM-R. Yeah, I would have actually used the quaternions, so it's kind of interesting that the first two columns of the rotation matrices are better than quaternions. Okay, they're saying here that quaternions and axis angle introduce discontinuities. Okay. So they're also giving the policy the linear and angular velocity of each of the links. Okay, so there's a lot of stuff here, right? In total, the simulated avatar has over 312 different inputs, right? This OSIM here that is coming. So, for example, OUser, the headset, is 6 degrees of freedom times 1 headset and 3 controllers. So total of 18 numbers is OUser. OSIM, which represents the physical avatar in the avatar in the physics simulation, right? We've seen here it has over 312 different things. It has the joint angles, it has the joint angle velocities, it has the Cartesian positions of the joints, it has the 2 first columns of the rotation matrices, and it also has the linear and angular velocity of each of the links. So there's a lot of stuff being fed here. It's a really rich signal coming from the physics simulator into the policy. I'd be curious to see if you actually looked within the weights of this neural network policy, how many of these inputs are actually being zeroed out, right? Is there an ablation study that was done to say, hey, actually it turns out that the rotation matrices are much more important than the joint angle velocities, or maybe the joint angles are much more important than the angular velocity of each of the links. I'd be curious to see which one of those are more important, or which one of those the policy decided are more useful. All right, synthetic training data. Yeah. Okay, so they have a bunch of mocap data, right? 8 hours of motion clips, 172 different people, 130 minutes of walking, 110 minutes of jogging, 80 minutes of casual conversation, 90 minutes of whiteboard, 70 minutes of balancing. So they created a mocap data set within Facebook. So in Reality Labs research, somewhere in an office in the Bay Area, they generated these 8 hours of mocap data. And the problem is that there is no head position, right? It's like you need the mocap data, but you want the position of the headset and the hands. So they just took this generic mocap data and then said, okay, we're going to take the position of the head and the wrist, and we're going to basically pretend, we're going to emulate the position and orientation of the headset left and right controllers. So one of the problems with this is that the position of the headset relative to your head actually changes, right? So in this situation here where this guy is running, right, that headset is going to kind of bump and a little bit as he runs, right? And the relative position of the headset position to the head pose, right, headset pose to head pose, is going to change over time, and it's actually going to be dependent on the animation. So that's maybe an extra thing they can take into account, a reason to collect kind of a data set. Although maybe as you get headsets that aren't as front heavy, right? The Quest 2 is kind of heavy it is heavy, and it's very forward bias, so it is more prone to kind of bouncing than something like a Quest Pro, which is more balanced on your head. Okay, position and orientation of the headset, left controller, right controller. Okay. So you have headset relative to frame S, right? The kind of global frame. First two columns of the orientation matrix of the headset, the left controller position, the first two columns of the left controller orientation, the right controller, and then the first two columns of the right controller orientation. So 6 future user observations. This gives us the ability to better anticipate Okay, so actually we were wrong. So remember here when we said that OSIM is 312, but OUser is going to be 18 numbers? Well, actually, because the position is 3, but they're also representing the orientation rather than with 3 numbers, right? Or 3 numbers, such as the Euler angles, or 4 numbers like a quaternion. They're representing it as the first 2 columns of a rotation matrix, which is 6 numbers. So this is now 3 numbers, 6 numbers, 3 numbers, 6 numbers, 3 numbers, 6 numbers, right? 3 plus 6. But they're also doing it for future poses as well. So the total dimensionality of OUser here is actually much higher. It's something like 162. Okay. So again, they say that the scale of the user is going to change, right? By scale, they mean kind of the height. Generate individual policies per scale. Yeah, so we give the policy access to the user scale in the form of a scalar value, so R. One dimensional, right? So this has 162 dimensions, this has 312 dimensions, and the user scale is just one dimensional. Where do they get this scale? We use the first pose in the clip, which is an A pose, to extract the height of the subject. Yeah, so A pose, I guess, is the new T pose. T pose to A pose. During inference, we require the user to stand initially upright, and the height is estimated based on that. Okay, so we've learn about the different inputs to the policy, right? This O of T, which is composed by a 312 dimensional, a 172 dimensional, and then an additional 1 dimension for the scale of the user. All of that gets fed into a policy that produces actions. And again, this actions given a certain observation is going to be trained as if it was a reinforcement learning problem with proximal policy optimization as the algorithm. So for reinforcement learning, right, you need a reward. Imitation reward, right, where you want the output of the policy to exactly match what you have during training. Okay. So Q again is the joint angles, and then Q dot is the joint velocities. X is the positions, and then X dot is the velocities. So here they have the difference of joint angles and joint velocities between the simulated avatar and the ground truth mocap pose, right? And same thing for the positions and velocities. So they're basically taking the ground truth, right, the expert policy that you're trying to imitate, which in this case is just the ground truth of whatever animation in that mocap dataset, and then the reward is how close the current position of the simulated avatar is to that ground truth position, right? So it's really just supervised learning. But they are saying here that actually they're using a Gaussian kernel. So it's not, yeah, they're taking the representation of the sim and the ground truth, subtracting it, L2 loss, and the sum over all of the joints J. Weights W and kernel sizes K can be found in the appendices. Okay. Okay, so there's an additional reward term here, which I think they're calling reward force, right? So you have the ones that are just tracking the position and the velocity of the joints, and the position and velocity of the Cartesian positions and the velocity of each joint, and then the joint angles and joint angle velocities. And then you also have this RF term here, which they explain here, which is basically the force. It's kind of like an additional regularization term that penalizes an abrupt decrease in vertical contact force, Fy. So if Fy at a previous step compared to the current step, if the contact force, vertical contact force Fy, which is this red little cylinder here in this picture, right? If that contact force changes drastically from step to step, the reward, you're going to get a large negative reward. So the policy is incentivized to keep that contact force as stable as possible. Policy directly outputs torques instead of PD target angles, which tracks stability, stably and reduce code complexity. "36 frames per second. I'd be curious if they ran this directly on the Quest. That would be really impressive, but I'm assuming that's 36 frames per second on a computer to which the Quest is connected. Downsampling of the HMD sensor data. Okay, that's interesting. So the Quest 2 outputs the position and orientation of the controllers and the head-mounted display, head-mounted device at 72 frames per second. They use NVIDIA's PhysX as the simulator, which has been wrapped by the RL training framework Isaac Gym. Okay. Isaac Gym, so NVIDIA's physics simulation for reinforcement learning research. Okay, so this is basically, you see here some Panda robots. Here you have the shadow hand in OpenAI's Rubik's Cube, juggling, manipulation. Here you have a bunch of quadruped robots navigating over an environment. Physics simulation runs on the GPU. Okay, storing results in PyTorch GPU tensors. That's very useful. Okay, and because you're doing this in the GPU in PyTorch, you can run thousands of environments in parallel. So this is huge for reinforcement learning research, because in reinforcement learning research, you have this kind of alternating training process where you have to basically train the policy, and then once you have a new version of the policy, then you have to collect a bunch of data in an environment from that policy. And those two things are different, right? Training is you're basically pushing gradients into a neural network, and that you're using a GPU, you're using it, doing it in batches so that it's efficient. But a lot of the actual simulating of a policy inside an environment, that's not accelerated with GPUs, right? That's usually, you have to do that across a bunch of different machines, and it takes more time. But here with NVIDIA's Isaac Gym, you can do it kind of the same, like you can do it in batches, right? The same way that you would do gradient descent. I don't know exactly how this works, but seems cool. Access to the simulation data using PyTorch tensors. Okay, this is the PPO implementation that they're using. 4,000 characters in parallel on an NVIDIA 3080. 14 billion policy steps, 13 years of human experience in 48 hours, right? The power of kind of being able to do this all in parallel on a GPU is huge. Okay, so now we get into the results section where we're going to look at the pretty pictures and kind of compare the results to maybe other approaches, and hopefully they have some ablation studies here. Okay. Tracking accuracy. We evaluate on synthetic input generated from the Laufen dataset, so they take real data recorded. Okay, so HMD and controllers, that's what H plus 2C works. So this is head-mounted display and the two controllers. And this is Laufen, so this is evaluated on the Laufen dataset, which isn't for a headset and controller, so they basically do the same way of generating synthetic data for that. Here you have just the headset and 6 IMUs. We compare our metrics to a state-of-the-art solution which uses 6 IMUs to attach to the legs and evaluate it on the total captured data set. So TC is another data set. So PIP is another tracking algorithm, I suppose. Okay, different metrics here. So these are the metrics on the left. So we have mean per joint rotation error. Lower is probably smaller. Smaller is better, but I mean, there's nothing to even compare it to here, so cool. It looks like it works great. 5.7 degrees of error. MPJPE, mean per joint position error in centimeters. So how far off in centimeters? 3.7. So it's off by something like that. 3.7 centimeters. Global root error in centimeters. SIP, which is the mean orientation error in global space in degrees. Jitter represents smoothness, so the smaller the better. So you can see maybe here's one point of comparison. The extra 2 controllers here, so headset versus headset plus 2 controllers, you get 1/2 of the jitter. It's qualified by the jerk. Mean headset position and rotation error, MHPE and then MHRE. Okay, so actually no real difference in position error with the controllers and rotation error. So this is actually quite interesting here. We see that the controllers are not actually doing that much. They're not giving you that much information. And I think part of that probably has to do with the fact that really all the position of the controllers are giving you is the position of the arm, right? Most of the human arms can move independently of the rest of their body, right? And all the joints in the body, right? Everything from the ankle to the knee to the hips to the shoulders to the chest to the head to the neck, all of that is really more a function of where your head is. And the arms are separate from that. So it kind of makes sense that, especially if you're looking at a data set that considers the entire body and right, this mean error, these mean position and rotation errors are going to account for the entire body. It makes sense that adding the 2 controllers and then giving yourself a little bit more fidelity for the arms is not actually going to give you that much better of a mean error, because a lot of that mean error is more to do with the head position and the knee position. There's more joints that depend on the head. Okay. We discussed 3 applications. The main application is using Sparse sensor information to reconstruct full body poses. Same policy can be used to track users of different scale. Modify track motions. Okay, that's kind of cool. Okay. Framework can distinguish between different types of motion. Yeah, so this is kind of what we're talking about here, is there's a little correlation between the controllers and the head. Okay, they have some difference in the users, different sizes without retraining. I think that's just because they're conditioning it on the height, so it's not, doesn't make any sense. I wouldn't Yeah, this seems like they're kind of embellishing that. Avatars of different scale to track the same user. Okay. Interesting. So, figure 5 here. So, if you tell the policy this user is 167 centimeters, and that's the actual height of the person, then you're going to get something a little bit more true to the actual what the human's doing. But you can actually retarget and say, hey, this user is actually 190 centimeters, and then you notice that the policy is saying, okay, well then he must be crouching. Okay. With, and then where does this paragraph continue? This naive baseline. Yeah, this is kind of, I think, another cool area of research. Is basically a lot of this, again, is a lot of this type of research is still trying to solve the problem of like, hey, if we have an avatar that's pretty close to what the actual human is, can we make sure that the tracking and motion is as accurate and good as possible? But I think in the future of this kind of metaverse world that we're going to have, I think your avatars are going to be much more different, right? You might even want a centaur avatar, right? And at that point, how are you going to track a user's motion to this kind of centaur character that has completely different bones and bones that don't even exist yet, right? Like the back of the back part of the horse. So motion retargeting for vastly different avatars is going to be interesting. Qualitative evaluation of post-reconstruction of motion sequence not used during training, corrected for latency. So they have here some different motions and kind of showing you really what you're looking for here is good correspondence between the top image and the bottom image. And of course these are going to be cherry picked, so they don't really mean anything. Okay, and then because this is a physics simulator, right, they can, for example, here the human is running on flat ground, so the position of the foot is always actually flat. It's always at the same position because it's flat. But in the simulated world, you can create this kind of rough terrain that is going to have a different, right, whenever you run on that, the angle of your foot is going to be different, the placement of your foot. And, right, they kind of talk about how the motion is adapted to match the virtual world, right? And that's really the result of this RF here, right? The kind of regularization loss, although it's a reward that rewards maintaining a kind of vertical contact force with the world. Okay, so this is probably a video. I don't know where the video is. Oh, see the video for more examples. Okay, so here they're training the policy, right? This is kind of showing you how they can train it in lots of different agents in parallel. Right? The contact forces of the feet, the pose of the controllers, the pose of the headset, moving. Kind of interesting. There's headset only. Right, the arms are kind of idling along. Environment interaction and adaptation. So it kind of shows you how right, here's the example we were talking about here with the feet, where like this guy's feet are always flat relative to the ground, but here the feet kind of adapt relative to the environment. Yeah, this poses a good question here, and this is how much should this semi-autonomous avatar be controlled by physics, and when should physics be violated to track the user? So, right, I think this is the best example of that. So like you had this human here, and in this case, the human runs into this box here, and the avatar falls over. And I think really the behavior you would want in a metaverse context is for the avatar to kind of like phase through that box. I don't think you actually want the avatar to interact with that box and fall, because that's the kind of true physics behavior. So I think that in that case, physics should be violated to more closely track the user. Yeah, they're basically saying simulated collisions and gravity can correct the track to avoid penetration or hovering. So if you have your hand and then you're moving it down into a virtual table, your hand in the real world won't stop, but the virtual hand will stop at the table, right? So that's kind of a version where you would want to have the avatar more controlled by physics than the user. Yeah, so character drifts further from the user, kind of like some of the standard errors or standard problems that you have with these things. Yeah, kind of upper and lower body not being correlated, and that kind of making it harder, especially when you're using these kind of data sets, mocap data, where upper and lower body motions are very correlated, right? It's like there is bias in that data set where specific upper body motions are going to be correlated to specific lower body motions, and creating a data set where all of that is uncorrelated, I think, is important for this type of research. GAN-based approaches. VFX quality animations. That's really what you need right there. Latency of 160 milliseconds, that's a lot. Yeah, so this is true too. Different humans have different proportions, so their legs relative to their arms, relative to their torso, relative to their neck, and so on. Eventually you would want the dimensionality of this here. It wouldn't just be a one number that represents your height. It would be possibly even hundreds of numbers that represent the relative size of all your joints and links to each other. Mixture of expert policies. That's kind of the engineering hammer, to be honest. When you have a bunch of algorithms that all work well but each have their own slightly different issues, you can combine all of them and then, in a sense, feed them into something that looks like a Kalman filter, right? Not in the same way, you wouldn't actually use a Kalman filter, but aggregating all these different outputs from these different experts in what's known as a mixture of experts is a way to kind of get the best out of all of them. Cool, and then below here, every 36 seconds, MLP, right, really pretty small, 400, 300, 200. This kind of annoys me. I would have done 256, right? Although I don't think it actually matters. They add Gaussian exploration noise, right? Because you're doing RL. Yeah, the output of the policy, right? As with anything deep learning, you're going to want to kind of normalize it to something like 0 to 1 or -1 to 1, and here they kind of choose this normalization. Newton meters is what you measure torque in. So these are the different reward weights, right, for that reward function. So quite interestingly here, right, this first term 4 times more important than, so if we go back to our reward here, we have joint angles, joint angle velocities, positions, and position and velocity. So the joint angles are the most important by far. The joint angle velocity is actually not that important. And the force reward is much higher than, for example, the Cartesian velocities or the joint angle velocities. Discount factor, this is actually kind of low. I've seen 0.99 kind of a lot. The discount factor is going to depend on kind of the step size of your environment and a bunch of other things. These are usually kind of tuned for specific environments. All right, guys. That's it for today. We went over QuestSim, human motion tracking for sparse sensors. Pretty cool paper coming out of Reality Labs Research, which is Meta's VR division. Cool. If you guys have any suggestions for papers I should read, let me know in the comments below, and see you guys later.